Welcome back. In this video, we will look at examples of determining the convergence of sequences using limits. Let's get to it. All right, so here's our first example. We have the sequence a sub n is equal to 3. And so if we want to determine the convergence of this sequence, what we can do is take the limit of the sequence as n approaches infinity. And so in this case, we would have the limit as n approaches infinity of 3, and the limit of a constant is always just equal to that constant, and so this is equal to 3. And so what this tells us is that this sequence converges to 3. As you would write out more and more terms, you would find that the terms would be leading to 3. And this makes sense because this sequence is just 3, and so every single term is going to be 3, right? If we were to write out some of the terms, a sub 1, where n is equal to 1, would be 3, a sub 2 would also be 3, and a sub 3 would be 3, and so on. Okay, so since there's no n in this sequence, no matter what value of n we use, the term of the sequence will still be 3, and so it makes sense that it converges to 3. Now if we look at our next example, we have the sequence a sub n is equal to 3 times n, and so if we want to determine the convergence of this sequence, we can take the limit as n approaches infinity. So we have the limit as n approaches infinity of 3n, and if we were to look at this expression as n approaches infinity, well, this whole expression is just going to increase towards infinity, right? As you pick larger values of n to plug into this expression, that expression will become larger. And so we would say that this limit is equal to infinity, and since that is an infinite value and not a specific finite value, we cannot say that this sequence converges. In fact, we would say that it diverges. All right, so what that means is that if we were to write out the terms for this sequence, and we were to look at what happens to those terms as we write more and more of them out towards infinity, you would find that they would not converge to a specific value. And you could see that if you were just to write out a few terms. If n is equal to 1, you have 1 times 3, which is just 3. So your first term would be 3. Then if n is equal to 2, you would have 2 times 3, and that's equal to 6. And then you would have 3 times 3, which is 9. Then 3 times 4, which is 12. And then you could continue on with more values of n towards infinity. But as you can see, each term is just increasing by 3, and this could continue on forever. And so our terms are just getting larger towards infinity and are not converging to a specific value. All right, so here's our next example. We have the sequence a sub n is equal to this list of terms. We have 0, 1, 2 to the third power, 3 to the fourth power, and then 4 to the fifth power, and then this would continue on from there. And so in this case, we aren't given an expression for the nth term of our sequence, we are just given some of the terms of our sequence. And so if we want to determine the convergence of our sequence by using a limit, we first need to write out that nth term that would represent all of the terms of our sequence. And so the way we're going to do that is by looking at our given terms and trying to recognize a pattern of some kind. And so let's write out our terms. We know that unless stated otherwise, our sequence starts at the value of n equals 1 and continues on to infinity. So we know that a sub 1, our first term, is equal to 0. That's this term right here. And then a sub 2 will be equal to 1. A sub 3 will be equal to 2 cubed. A sub 4 will be equal to 3 to the fourth power. And a sub 5 will be equal to 4 to the fifth power. All right, and so now that we have all of our terms written out, let's see if we can find some kind of pattern for these terms with regards to the value of n for each term, and that should help us determine how to write out our nth term. Now for 3 of these terms, I see we have an exponent. Specifically, the exponent is increasing by 1 with each term, right? We have 3, then 4, then 5. And so let's see if we can rewrite our first 2 terms in some way to match that pattern that these other terms have of those exponents. And so since it's increasing by 1 each time, that means that this term should have an exponent of 2, right? We should have 1 squared, and 1 squared is equal to 1, so this checks out. This is the same thing as just having 1. And then if we decrease the exponent by 1 again, we would have 0 to the first power, and anything to the first power is just itself, and so this would still be equal to 0. And so this is a valid way to rewrite 0. And so now all of our terms have this pattern where the exponent matches the value of n, right? We have a sub 1, where n is equal to 1, and we have 0 to the power of 1. Then we have a sub 2, where n is equal to 2, and we have the power of 2. And then when n equals 3, we have the exponent of 3, n equals 4, exponent of 4, and n equals 5, exponent of 5. And then you'll notice that the value that is being raised to those exponents is 1 less than the value of n, right? When n equals 1, we have 0 to the first power. When n equals 2, we have 1 to the second power, and that continues on for the rest of the terms where the value being raised to the power is 1 less than the value of n. And so what we can determine is that a sub n is going to be equal to n minus 1 to the power of n, right? We have a value being raised to a power where that value is 1 less than the value of n, and they're being raised to the power of n. And so this is the nth term of our sequence. And so now we can use this expression to determine the convergence of the sequence by taking the limit of a sub n as n approaches infinity. And so if we do that, we'll have the limit as n approaches infinity of n minus 1 to the power of n. Now if we look at this expression as n approaches infinity, we have n minus 1, and so if this n is increasing towards infinity, then it will become infinity, and we're just subtracting 1, and so that would still be infinity, and so this is equal to infinity, but then it's raised to a power of n, and if n is approaching infinity, then that exponent will also approach infinity. And so we have infinity to the power of infinity, and if you raise an increasing value to a power of an increasing value, it's just an increasing value, and so infinity to the power of infinity is just a value that is getting larger, and so we would say that that's just equal to infinity. And so what this tells us is that this sequence, as we write out more and more terms, the value of those terms is just getting larger and larger towards infinity, and it's not converging to a specific value. Okay? So when your limit is infinity, you know that your sequence does not converge. Instead, our answer is that it diverges. Okay? So this sequence that we were given, that we wrote out the nth term for, of n minus 1 to the power of n, is a divergent sequence. Here's our next example. We have the sequence a sub n is equal to the natural log of 6n divided by the natural log of 2n. All right, and so if we want to determine the convergence of this sequence, we need to take the limit as n approaches infinity of our sequence. And so if we do that, we'll have the limit as n approaches infinity of the natural log of 6 times n divided by the natural log of 2 times n. Okay, and so if we look at this expression, as n approaches infinity, what's going to happen in the numerator and the denominator? Well, if this n approaches infinity, it's going to get larger and larger, and then we're multiplying it by 6, and so we just have a value that is increasing within the natural log function, so you could say that this is infinity, and as the values that are inputted into the natural log function increase towards infinity, the natural log function is going to output larger and larger values. And so you would say that in the numerator, that is approaching infinity, and the same is going to occur in the denominator because we have the natural log of 2n. It doesn't matter what you multiply n by, that value is still increasing because n is approaching infinity, and if you plug larger and larger values into the natural log function, once again, it's going to output larger values. And so we also have infinity in the denominator, and so we have an indeterminate form of infinity divided by infinity that is compatible with L'Hopital's rule, and so we can simplify this limit by using that rule and taking the derivative of the numerator and the denominator, and that should help us evaluate our limit and determine if this sequence converges. And so if we take the derivative of the numerator and denominator separately, we will have that this is equal to the limit as n approaches infinity of the derivative of the natural log of 6n. And remember, when you take the derivative of a natural log function, you will have 1 divided by the inside function times the derivative of that inside function. So we have 1 divided by 6 times n times the derivative of 6n, which with respect to n is just 6. And that will be divided by the derivative of the natural log of 2n, which will be 1 divided by that inside function of 2n times the derivative of 2n, which is going to be 2. All right, so now that we have taken the derivative of the numerator and denominator, let's simplify. We have 1 divided by 6n times 6. Those 6's will actually cancel out. And then in the denominator, we have 1 divided by 2n times 2. And those 2's will cancel out. And so this is equal to the limit as n approaches infinity of 1 divided by n divided by 1 divided by n. right? When we cancel out those 6's and 2's, all we're left with is 1 divided by n in the numerator and the denominator, and 1 divided by n divided by itself is just equal to 1, and so this is equal to the limit as n approaches infinity of 1. And the limit of a constant like 1 is just going to be equal to that constant, and so the limit is equal to 1. And so what we learn from that is that our sequence is going to converge to 1. And so we want to write that down, that our sequence converges to 1. And so what that means is that if we were to write out the terms of our sequence, each subsequent term would get closer and closer to 1. So our sequence converges to 1. All right, so here's our next example. We have the sequence a sub n is equal to cosine of n divided by n. Now, if we want to determine the convergence of this sequence, we need to take the limit as n approaches infinity of the sequence. So we'll have the limit as n approaches infinity of cosine of n divided by n. All right, and so if we look at this expression as n approaches infinity, what is going to happen in the numerator and in the denominator? Well, in the numerator, we have cosine of n, and as n approaches infinity, something weird is going to happen with the cosine function. If you're familiar with the cosine function, you know that if you were to look at the graph, between the values of positive 1 and negative 1, the cosine function is going to oscillate. It's never going to be larger than positive 1, and it's never going to be less than negative 1. And so because of that, we know the numerator is always going to lie between those values. But what about the denominator? As this n approaches infinity, that whole denominator is just going to increase towards infinity. And so we know that when we have a fixed value, and remember cosine of n is going to be between negative 1 and 1, and that fixed value is divided by an increasing value, that the limit will be equal to 0. And so we know that this limit will be equal to 0, that this sequence is going to converge to 0. But how can we show that? Well, what we can do to prove that the limit as n approaches infinity of cosine of n divided by n is equal to 0 is make use of a special theorem known as the squeeze theorem for sequences. And so the squeeze theorem for sequences says this: if we have three different sequences, a sub n, b sub n, and c sub n, where a sub n is less than or equal to b sub n, which is less than or equal to c sub n, meaning that this sequence b sub n, its terms are greater than or equal to the terms of this sequence, but less than or equal to the terms of this sequence, so it lies in between them, then if the limit as n approaches infinity of the first sequence, a sub n, is equal to the limit as n approaches infinity of c sub n, the last sequence, and both of those limits are equal to L, a limit that exists, then the limit as n approaches infinity of b sub n, our middle sequence, will also be equal to that same limit L. Right, so what this theorem allows us to do is if we have the limit of a sequence that we're not quite sure how to show that it is equal to a certain value, we can find two other sequences, one that is less than or equal to our sequence and one that is greater than or equal to our sequence, and if those two sequences have the same limit, then we can conclude that the limit of our middle sequence, the one we're trying to determine, will also be that limit. And so if we go back to our example, if we want to prove that this sequence, cosine of n divided by n, converges to 0, we just have to pick a sequence that is less than or equal to that sequence, and a sequence that is greater than or equal to that sequence, and show that those two sequences also converge to 0. But what two sequences could we pick? Well, remember what I said about cosine of n, that cosine oscillates between 1 and negative 1. And what that means is that this numerator will never be greater than 1, it can be less than 1, but it will never be greater than 1, and it will never be less than negative 1. It might be greater than negative 1 at some points, but it will never be less than negative 1. And so we could say that our sequence cosine of n divided by n is greater than or equal to negative 1 divided by n, but less than or equal to positive 1 divided by n. Right, so we keep that denominator the same, but since we know that cosine of n is going to oscillate between negative 1 and 1, and it will never be greater than 1 or less than negative 1, then we can say that that sequence is between those two sequences. And we know what the limit is as n approaches infinity of these two sequences. We know that the limit as n approaches infinity of negative 1 divided by n will be equal to 0, because as the denominator increases towards infinity, we have negative 1, a fixed value divided by an increasing value, And so as that denominator gets larger, this whole fraction gets smaller towards 0, and so the limit is equal to 0, and the same will be true for the limit as n approaches infinity of positive 1 divided by n. That will also be equal to 0. As that denominator gets larger towards infinity, that whole fraction gets smaller towards 0. And so since the limit as n approaches infinity for both of these sequences, that cosine of n divided by n lies between, are equal to 0, then the limit of this sequence must also be 0. All right, and so by using the squeeze theorem, we were able to prove that our sequence converges to 0. The limit of our sequence is 0, which means that it converges to 0. All right, so as you would write out more and more terms of this sequence, you would find that each subsequent term gets closer and closer to 0. All right, so here's our next example. We have the sequence a sub n is equal to this list of terms: negative 1/4, positive 1/16, negative 1/64, and positive 1 divided by 256. And so this is similar to one of our previous examples where we don't have the nth term of our sequence written out for us. We instead have a list of terms. And so what we want to do before we can determine the convergence of our sequence is first write out that nth term to represent the terms of our sequence. And so in order to figure that out, let's write out what our terms are. We know that a sub 1 will be equal to negative 1/4. A sub 2 is equal to our next term, which is 1/16. So we have 1/16. Then a sub 3 is equal to negative 1/64. And a sub 4 is equal to 1 divided by 256. All right, and so now what we want to do here is look for a pattern within our terms. Now in the numerator, notice that we have negative 1, then positive 1, then negative 1, then positive 1. When you see that a value is oscillating between being negative and positive, like these terms are, you know that it involves this expression of negative 1 to the power of n, right? Because when this power is an odd number, it will just be negative 1, but when this power is an even number, then it will be positive 1. And so when n equals 1, we have negative 1, because 1 is an odd number. When we have n equals 2, we have positive 1, because 2 is even. And then for n equals 3, 3 is odd, so we have negative 1. And then n equals 4, 4 is even, so we have positive 1. So we know that negative 1 to the nth power is in the numerator of our nth term. So we have a sub n will be equal to this expression. But what about the denominator? Well, we have 4, then 16, then 64, and then 256. Now, if you're familiar with the powers of 4, maybe you can already see the pattern here. This is equal to negative 1 divided by 4 to the first power. This is equal to 1 divided by 4 squared. This is equal to negative 1 divided by 4 cubed. And this is equal to 1 divided by 4 to the fourth power. All right, so 4 is just 4 to the first power, 16 is 4 squared, 64 is 4 cubed, and 256 is 4 to the fourth power. Okay, and so then notice that each of those powers matches up with the value of n for each term, and so we can say that the denominator is 4 to the power of n. Okay, so when n equals 1, we have 4 to the first power, n equals 2, 4 squared, n equals 3, 4 cubed, n equals 4, 4 to the fourth, and so on. And so this represents the nth term for our sequence in this example. Now, if I clean up my work, we can determine the convergence of the sequence by taking the limit as n approaches infinity. And so if we do that, we'll have the limit as n approaches infinity of negative 1 to the power of n divided by 4 to the power of n. Now, similar to our last example, we have a numerator that is oscillating between two values, right? Negative 1 to the power of n. As n approaches infinity, this does not reach a specific value. It doesn't really converge to anything. We can't even say that it's increasing towards infinity because this numerator is just negative 1 or positive 1. And so it's kind of hard to evaluate a limit when you have an oscillating value like that. And so although you may be able to look at this limit and say, well, the numerator is always going to be 1 or negative 1, but the denominator is increasing towards infinity, so this must be equal to 0, right? 4 to the power of n. If n is increasing towards infinity, this whole denominator is just going to increase towards infinity, and so we would have a fixed value divided by an infinite value, which would be equal to 0. But because of that oscillating value in the numerator, saying that this limit is just equal to 0 is not going to be good enough. We need to show that this sequence converges to 0 by using the squeeze theorem once again. Alright, and so what we want to do to use the squeeze theorem is find two sequences, one that is less than or equal to this sequence and one that is greater than or equal to this sequence, and show that they both converge to 0, which means that this sequence would also converge to 0. And now this is going to be very similar to what we did in the previous example. Since we know that the numerator oscillates between -1 and 1, and it's never going to be less than that or greater than that, then we know that -1 divided by 4 to the power of n will always be less than or equal to -1 to the power of n divided by 4 to the power of n. And that will always be less than or equal to +1 divided by 4 to the power of n, right? If we keep the denominators the same, and we're just looking at the numerators, the only two values that this can be is -1 and 1, so it's either less than or equal to 1 divided by 4 to the power of n, and it will always be greater than or equal to -1 divided by 4 to the power of n. And so if we look at the limit as n approaches infinity for those other sequences, we have -1 divided by 4 to the power of n, and the limit as n approaches infinity of +1 divided by 4 to the power of n, both of these limits are just equal to 0, because we have a fixed value divided by a denominator that is going to increase towards infinity. 4 to the power of n, as n increases to infinity, will just make that whole denominator infinity. It will get larger and larger, and so we have a fixed value divided by an infinite value for both limits, which means they're both equal to 0. And so because both of those sequences will converge to 0, that means that this sequence must converge to 0 as well. And so from this work that we did using the squeeze theorem, we can determine that our sequence converges to 0. Here's our last example. We have the sequence a sub n is equal to n minus 2 quantity factorial divided by n factorial. Alright, now this sequence might seem pretty complex, but what you're going to find is that this is not as bad as it looks. So if we want to determine the convergence of this sequence, we need to take the limit as n approaches infinity of that sequence. So we'll have the limit as n approaches infinity of n minus 2 factorial divided by n factorial. Now before we try to ask ourselves what happens to n as it approaches infinity for this expression, we can actually simplify this a little bit. We can simplify n factorial to force a cancellation with the numerator. And so here's what I mean. Remember that 3 factorial is equal to 3 times 2 times 1, right? So each subsequent factor is 1 less than the previous. And so n factorial would be equal to n times n minus 1 times n minus 2, and we could continue on forever. But if we stop there, we could just say that we're multiplying by n minus 2 factorial, right? We could do the same thing for 3 factorial. Instead of writing 3 times 2 times 1, we could just say that this is equal to 3 times 2 factorial, because 2 factorial is 2 times 1, so we can stop it at any point. And for another example, we could do this with 4 factorial as well. We could say that that is equal to 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. So you can stop at any factor you'd like, and then just put that factorial on the end, and they're still going to be equal. And so that's what we're doing right here. For n factorial, we have n times n minus 1 times n minus 2, and then we're going to stop there and just put a factorial for that last factor. And so the reason why we want to do this is because if we replace n factorial in our denominator with this expression, n minus 2 factorial will cancel out with the numerator. And so what we'll have is that this is equal to the limit as n approaches infinity of n minus 2 factorial divided by n times n minus 1 times n minus 2 factorial, and those factors will cancel out and just leave us with the limit as n approaches infinity of 1 divided by n times n minus 1. Okay, and so by doing that, we completely eliminated the factorials from our limit, and now we just have a limit of a simple rational function. All right, so now we just have the limit as n approaches infinity of 1 divided by n squared minus n, if you distribute that n through this quantity. So now if I clean up my work here, we now have a limit that we can evaluate. Maybe you can already see that this will be equal to 0 because our denominator will be infinity, right? As n approaches infinity, n squared is going to get larger and larger, but faster than n. And so we would have infinity in the denominator, but we could also solve this using one of our older techniques from Calc 1 of multiplying by a form of 1 of 1 divided by the highest power found in the numerator or denominator. And so in this case, that is n squared. So we would have 1 divided by n squared divided by 1 divided by n squared. And that will give us the limit as n approaches infinity of 1 divided by n squared divided by 1 minus 1 divided by n. Right, n squared times 1 divided by n squared will be 1, and then n times 1 divided by n squared will be 1 divided by n. And we know that the limit of 1 divided by n squared is 0, and 1 divided by n is 0, and so this is equal to 0 divided by 1 minus 0, which is equal to 0. And so, since the limit is equal to 0, we know that this sequence converges to 0 as well. And so, that is the final solution for this example. And so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.